interactive because there are problems with the translation of different terms. So if you see that a term on the screen, this is an international term, try to memorize them, because in the Russian language we have problems with it, and he will be talking about what these terms mean, because there is no adequate translation in the Russian language, and it's a difficult job for our interpreters to translate that into the Russian language. But when you are reading the publications, such phenomenon and different measures like Occurrence, and then it's very difficult. It's difficult to translate that into Russian, but in publications they will be in English still, and we plan to publish that in English. So try to memorize that in the original, in English language.
Now I'll try to talk about the first steps in the journey that will hopefully end up in a publication in a major journal such as Asian Journal of Cancer Prevention.
Let's not be facetious.
So I think these are sort of the basic issues that whenever you have collected the data, I urge you to do systematic, comprehensive data on your own patients. So when you start analyzing the data, whatever the purpose is, you'll have, and it's epidemiology, then you'll probably have to deal with occurrence measures. And if it's analytical study addressing a question of effect, cause and effect, then you'll have to also deal with effect measures. And I just listed some of the vocabulary that Anton is busy translating into Russian about some of the things that we'll be talking about during the next 40 minutes. Basically, occurrence, to me anyways, it indicates how common is the disease. For an epidemiologist that is interested in counts, probabilities, risks, we are talking about frequency of outcome events when we're talking about occurrence, disease events, and most commonly they are binary, yes or no, does this person have the disease or not. Of course, you can sometimes classify them more into mild disease and severe disease, or if it's a blood pressure, you can have the continuous measure or serum cholesterol or other measures. But here I'll talk about occurrence in terms of events, which require that they are dichotomous. When we talk about occurrence, we need a numerator and a denominator for whatever purpose and whatever measure we are using. And then those we try to use in order to calculate risks, probabilities, and rates, which then indicate us the effects that we're interested in. But let's start from very basics. This sort of circle represents population. And then this is the very first step. You should know the population, where are, for instance, the patients coming from, how many people are there that would seek treatment if they had the disease. So this is the very basics of epidemiology, which largely stems from demography and really is the study of population and epidemiology and disease in populations. So then within the population we have usually much smaller fraction than in this representation of people with the disease. And this is the first step in defining what do we mean with the disease. And ideally, of course, if we wanted to distinguish, identify everybody with the disease, we would need to administer the diagnostic test to each and every person in the population. But that's rarely possible. So typically we only rely on those people who have symptoms to seek medical attention and then undergo diagnostic testing. Of course, we do have some instances such as screening where we target the entire asymptomatic population, as much of the population as we can, and then we administer not a diagnostic test but screening test anyway, and then refer those with elevated risk of disease to diagnostic examinations. But okay, so we have a population, and within the population we have people with the disease. And we need to define what we mean with the disease, what kind of diagnostic criteria we are using as case criteria. Typically you would assume that most people with the disease are diagnosed, but there's an early stage when people do not seek yet medical care, and there will be undetected disease cases also in the population. And often if you are relying on treatment as an indicator of disease, for instance in Finland we have nationwide medication reimbursement register, and in order to qualify to that you need to fulfill the diagnostic criteria, and then anybody who is entitled to special reimbursement for medications will be in that register. But it's once again provided they have the disease, they are diagnosed and they are treated. So it does not really cover everybody with the disease. And then if you are interested in mortality or using mortality as a measure of disease occurrence, then there will likely be deaths in all of these three groups of diseased persons. As I mentioned, we have a population perspective in epidemiology, and we try to classify people into those with the disease and those without the disease, and this representation of these tan figures are free of disease, and these dark figures represent people with the disease. And for numerator, we need the numbers of disease cases, the case count, and then we need the denominator, the population size. And what is important in the very first stages is that the definitions match each other as perfectly as possible, so that anybody who would have the disease would be included as a case. If you have sort of people whose disease is diagnosed or treated elsewhere, then you do not have complete coverage of disease cases in your population, and then you will underestimate the disease frequency. Okay, so I'm trying to introduce some population terms, but I must warn you already that these are not very consistently used by different epidemiologists. Basically, what I would call the entire population as the base population from which we start. These are strongly influenced by Olli Miettinen's concepts of population. So the largest, the broadest population would be the base population. Within that, the researcher then selects who would be eligible for the study, the inclusion criteria, for instance, based on age or whatever other limits that the researcher chooses. And that I would call source population or target population, source of the cases or target of the intervention. And then finally, after the researcher has made the selection and tried to include everybody in that group in the study, typically not everybody who is invited will take part. So it will be incomplete participation, and once again, only a part of the population will be included in the study, in case any involvement from the study subjects is needed, obtaining a consent, filling in a questionnaire, undergoing a test or giving a blood sample or whatever procedures are required for collecting information for study purposes. And that I would call the study population, which is the population that you are able to use in your data analysis. And just an example, Nurses' Health Study, classical epidemiological study in the US. Basically, you could think of as the base population, all the female population in the US, which numbered 111 million at one point of time, and the age range included in the study was 30 to 55. Number of women in those ages was 31 million. Then the researchers chose to focus on licensed nurses, and they used eligibility criteria of being alive in 1976, having the age range mentioned earlier, being married, and resident in one of the 11 states where the study was conducted. So that was a restriction imposed by the researchers. And then finally, out of those 170,000 nurses, 122,000 participated. And this is a very high figure and that was one of the reasons why the researchers wanted to focus on nurses, because they would be interested in health and disease and therefore highly motivated to participate, and also able to give good quality data about their own diseases and lifestyles. Okay, after these very general terminological issues, we'll move on to occurrence, and the two basic occurrence measures that we use in epidemiology are prevalence and incidence, and both can be subdivided into two terms. For prevalence, we talk about point prevalence and period prevalence. So who knows the difference between these two concepts? It's all familiar to you? Ever heard before? Point prevalence, period prevalence?
Поднимите руки, кто знает, что такое point prevalence и разницу между period prevalence.
Could you please raise your hands, those who know the difference between point prevalence and
Period prevalence. Есть кто-нибудь?
Okay, somebody's been trained.
No one can answer this.
Okay, so I'll cover them also. Yeah. So basically, prevalence means the extent of disease that is present in the population. Here again, I assume that you either have the disease or you don't have the disease, so we can use this dichotomous classification. So for the cases that we use in order to calculate prevalence, we have to define the time period during which they have the disease. So if it's at one single moment of time, then we talk about point prevalence. Typically it will be 1 day, for instance, the time of the survey when people receive the questionnaire or a date defined in the questionnaire or telephone interview, for instance, or nowadays internet survey. Or alternatively, we can ask, have you had this disease during, let's say, the past 12 months? Then we talk about period prevalence for 1 year. And for example, we could ask, have you had a headache within the past 12 months? And then we talk about 12-month prevalence of headache, or low back pain, or whatever other conditions. And when we talk about prevalence, then the disease concept we are using is disease as a state, sort of a trait or feature, time-dependent characteristic of a subject. And for prevalence, as distinction from incidence, we don't pay any attention to the time of onset. It is whether or not you have the disease in a given moment. We are not interested in when the disease started. And prevalence is used mainly for long-standing chronic conditions, such as those that I mentioned, and is not suitable for frequent, quickly recurring conditions, such as, let's say, infectious diseases. Prevalence is usually expressed as a proportion, either as a percentage or between 0 and 1. The numerator here is people with the disease, and the denominator is the size of the study population. And then very simply you just divide the number of disease cases with the population size. While incidence, as distinction from prevalence, is an indicator of the frequency of new disease cases. So it's more about the disease dynamics, disease development. And if prevalence had to do with the disease state, then incidence is based on events. We think about disease onset as a transition from the healthy state to the diseased state. And once again, you need the case definition, you need the diagnostic criteria, and for calculating incidence, you're probably interested in disease cases that are diagnosed by the physician. But there are, for instance, validated questionnaires for assessing other for certain diseases, and of course, having blood pressure measurement, having cholesterol measured, and so forth, can also be used for defining a case. And incidence is difficult to use for diseases that have an insidious onset, so that the time of onset is hard to define, because we are interested in when did the disease first occur. And incidence we can break down into two concepts. One is incidence proportion, which is number of cases proportional to the number of subjects, just simply disease cases related to the population size, and that incidence proportion will give the risk of an event, just calculate from the frequencies, so that the numerator is number of new onset cases during the study period, and the denominator is number of people at a risk who would have been counted as cases if they had developed the disease. And for calculating incidence, you need to be at risk. Typically would mean that you are free of the disease at entry, at the start of the follow-up period. And then incidence proportion can be expressed similar to prevalence as a risk or probability ranging from 0 to 1 or as a percentage, and also calculated very similarly, the only difference being that here these are the numbers of new cases and not the existing cases as for prevalence. And the other type of incidence, probably more commonly used in epidemiology, is incidence rate or incidence density rate. And rates are always proportional to time, so they are sort of velocities. So we are talking about event rates. And here the numerator is identical to incidence proportion, but the denominator is not the number of people, but is the amount of person time at risk, number of observation time. Typically it's calculated as person years of observation. So basically you just sum up the follow-up times of everybody in the study population. And you start the follow-up from the entry, at the time when we start collecting the data for the study, until exit from the study, which could be through disease onset. You are no longer at risk of when you have the disease already, or at death, or loss to follow-up, or end of the study period. So everybody would contribute some time to the person time, observation time to the study. And here's just an example, just playing around with numbers. If we have data for 3 years, the study population is initially 1,600 people, and then there are some Alzheimer's disease cases and some deaths. So people exit the study either by contracting the disease or by being no longer at risk by virtue of being deceased. And the second year, after these people have left the study, the population size has decreased to 1,532. Once again, there are some cases, some deaths from Alzheimer's and other deaths. And then in the third year, once again, we have the study population diminished, new cases, deaths, and other deaths. So we can calculate, for instance, the prevalence during the third year. So we have, these are the cases that have been diagnosed during the 3-year period, minus these 3 who died from the disease already before, assuming that there are no other deaths here among cases of Alzheimer's. So it's 12 plus 15 plus 17, these case counts minus these deaths before the start of the year. So we have 41 cases, and then during that year we assume that we have full follow-up, 1-year follow-up for each and every member. So that would be 1,451 person years. Sorry, this is prevalence. So this is 2.8% would be the prevalence during the year 3. Incidence proportion, we would only take the new cases and not take into account the old cases, because incidence by definition covers only new onset cases. And so the incidence proportion would be smaller than the prevalence. And then the incidence density rate, we would calculate the person years as the number of people at the start of the year minus half of those that exited, by assuming that on average these people contribute only half a year follow-up time, based on the presumption that the deaths and the diagnoses are spread evenly throughout the year, meaning that on average they take place halfway through the year. And then we get the number of person years as 1407, and then we would get the incidence density rate as roughly 12 per 1,000 person years. A third measure of occurrence is odds. It's very rarely used. The Englishmen do use it, but not for disease measurement purposes, which is ratio of probability and its complement, usually presence of disease versus absence of disease. So if let's say we have, if we have 10% of people with the disease, so this would be 0.1, then the complement would be 0.9, so the odds would be 0.1 divided by 0.9. And this comes from betting world and not from medical world. But why we use it is exclusively for calculating effect measures in case control studies, not used for other purposes. Okay, just listed some types of diseases where you could apply various occurrence measures. I think, for instance, migraine, well, typically they would measure it as prevalence. What is the proportion of people in the population who have migraine attacks from time to time? You could use also incidence, but it would not be a good measure of the disease burden in the population, because typically migraine is a long-standing condition that people live with, and the disability is due to having this characteristic of being prone to having migraine attacks. Congenital anomaly, likewise, you are born with an anomaly, then the time of onset is hard to define, and also it is sort of a handicap that you'll live with. So therefore, incidence is not really a good measure. Low back pain, now you could use probably either prevalence, 1-year prevalence, or point prevalence, or alternatively incidence, assuming that you are not defining low back pain as the first time during your life, but let's say during 1 year. These are also a very episodic type of health event. Alzheimer's disease, I think probably all of them would be useful. Prevalence, incidence, and mortality. Incidence perhaps slightly difficult because the diagnosis can be tricky during the lifetime. Well, nowadays I guess MRI is helpful, but still the exact time of onset for Alzheimer's disease can be difficult to establish. Hip fracture, I think probably incidence. It is really a sudden health event, and therefore incidence would be a good measure. Hypertension, well, more like Alzheimer's disease probably. You typically would not be aware of when did your hypertension really start. So, but it's only the time that it's detected can be recorded, and therefore prevalence would be a good measure. Sinusitis, probably either prevalence or incidence could both be appropriate measures of the frequency. Pretty much like low back pain, I would say. Okay, and just playing around with numbers once again. These are cancer cases from Finland. Population in 2011 was about 5.4 million. There were nearly 30,000 new cases, and there were more than 11,000 cancer deaths. Numbers of people who had ever been diagnosed with cancer and who were still alive was close to 250,000, and the number of people alive who had been diagnosed within the past 10 years was 154,000. And once again, you can play around with these numbers and calculate various measures of disease occurrence. So that, for instance, prevalence, ever having had the diagnosis of cancer is the number of these people divided by the population size, and it is 4.5%. Prevalence during the 10 years, this would be period prevalence clearly, would be about 2.9%. Number of these cases divided by the population size. Incidence proportion you could also calculate from the numbers of new cases in relation to the population size, and you would probably come up with an estimate of mortality. You don't have the person years here, so you can't get an accurate estimate of mortality in relation to person years, but you can relate the numbers of cancer deaths to the population size. And in principle, you could also calculate the odds, but that's not really usable. Okay, so we've covered half of the topics now, the occurrence measures, and then we'll move on to how do we apply them in the analysis of the data, which is effect measures. So as this was shown already during the morning session, so in epidemiology you would typically be interested, or we would formulate the research question as a relationship between an exposure to the occurrence of disease. And we need, for any analytical study, we need to have measures of occurrence, which is health condition of interest or endpoint or outcome, however you'd like to call it. And with exposure in epidemiology, we mean any potential determinant of the outcome. Could be physiological measure of blood pressure, could be a genetic polymorphism, could be behavioral issue, smoking, or whatever. Basically, we just use this term to indicate that this is the determinant, the postulated determinant of the disease that we would be studying. Could be a treatment also. Okay, so I'm using once again a simplified schematic representation of a population. Let's say that we have this population and this fraction of it is exposed, the rest are unexposed, and once again the tan figures represent healthy people and the dark figures those with the disease. So when we are interested in an association, we are talking about the observed relation into data, as our Taiwanese collaborators, for instance, mentioned in the morning. And when we are interested in the effect of exposure on the outcome, we assume that there's variation in risk, and we try to identify which factors are associated with that variation. And it could be either an increase or a decrease in the occurrence. And in epidemiology, with an effect, we just mean that there is a comparative assessment of occurrence. We are comparing occurrence in one group with occurrence in the other group. And the basics is very simple. First, typically we would assess exposure to form groups for comparison. This would be typical for a cohort study. Then we would measure occurrence in groups with contrasting exposure. Then we would compare the occurrence measures, and then finally express this in terms of the chosen effect measure. And the effect measures, the effect can be defined as the difference that we observe due to a given factor, the exposure, and the effect measures are then just indicators that quantify that effect. And we obtain the effect measures by comparison. So what we're interested in is comparative effect. And the observed difference between the groups that we are contrasting indicates us the effect of the exposure. This is, of course, resting on the assumption that there are no other differences between the groups, and this is then the fine art of epidemiology, being able to form groups that really are similar in all other respects, or alternatively trying to synthesize what the rates or risks would have been if the groups had been similar. So this is then, I think, a bit more advanced than that we're going to talk about today. Okay. So the mainstay of sort of the philosophical thinking about causality in epidemiology nowadays rests much to counterfactual reasoning, which means that what would the effect be in the exposed group if there had been no exposure? So it's something that did not happen in reality, but something that we are trying to construct through conducting the study, including design and analysis. So that can be, I think, very well summarized as the objective of an epidemiological study, to be able to estimate if we observe this incidence, let's say, in a exposed group, then we try to also contrast what the incidence had been if there had been no exposure. And in a cohort study, we would typically have an exposed group, those with the determinant of interest, and those who did not have it. And then we would evaluate during the course of the study the occurrence of the disease of interest in the presence of exposure, and compare it with the occurrence of the same disease in the absence of exposure. And this would be then very fitting with the counterfactual model that I just mentioned. And in cohort studies, we are comparing occurrence directly, this is occurrence in one group, to the other. So the frequency of outcome in the exposed group can be indicated as conditional probability of the outcome given exposure. And in the non-exposed group, similarly, probability of the outcome given no exposure. And then we can simply just calculate the absolute effect as the risk difference or rate difference as the difference between the two measures of occurrence. The risk in the exposed group and the risk in the non-exposed group. Or alternatively, relative effect as the rate ratio or risk ratio by dividing one with the other. So that here the risk ratio, for instance, would be the number of cases in the exposed group, the number of people in the exposed group, number of cases in the non-exposed group, and the size of the non-exposed group. And then we have the risk in the exposed and risk in the non-exposed, and that would give us the risk ratio. And similarly, well, the epidemiological is like 2x2 tables, so just the same thing as a tabulation. So we have exposure, no exposure, disease, no disease. And this is a cohort study, so these are new incident cases, and so we can calculate the incidence proportion from the frequencies, numbers of subjects, and there we have the incidence proportion in the exposed group, those with the disease, and the total group size. Likewise, for the non-exposed group, number of cases, and the size of the group, and the rate ratio as the ratio of these two incidence proportions, or alternatively the risk difference by just subtracting the risk in the non-exposed group from that in the exposed group. So the algebra is not really demanding. Anybody can calculate those. So I return to this earlier example showing that we had this population divided in terms of exposure, and then we had a small number of disease cases. So we could easily calculate what is the risk among the exposed. Well, there are 8 people in this exposed segment. There are 2 cases among them, so that is a quarter. We can calculate the risk among the non-exposed. There are 32 subjects in this group, and there's only 1 case, so it's 1 per 32, which is close to 0.03. So the risk difference, very simply, you just subtract the risk in the non-exposed group from the risk in the exposed group, and the risk difference is 0.22. Or alternatively, you can calculate the risk ratio by dividing the risk in the exposed group with that in the non-exposed group, and you get the risk ratio of 8. An example, a real-life example, a bit more complicated than larger numbers that I've shown. This is from Lancet last year, an interesting paper on childhood leukemia, one of my hobbies. A Taiwanese cohort study, actually, where they were relating the risk of leukemia among children who have had an enterovirus infection and those who did not have enterovirus infection. And one of the key skills, of course, learning to read what does this mean. Okay, so we have the children who did have the infection and their cumulative incidence of leukemia. Well, we are talking very small numbers here. And then likewise, the cumulative incidence among those who did not have the enterovirus infection. And somewhat contrary to the study hypothesis, the risk was clearly higher in the non-exposed group. So leukemia incidence among the infected was roughly 3 per 100,000, while it was almost 6 per 100,000 among those who did not have the infection. So the hazard ratio, which is just sort of integral of risk, the hazard was 0.44, meaning that those with the infection had lower risk of leukemia, and it's statistically significant. Okay, more numbers. This is also a real study from the famous International Journal of Cancer that Malcolm was advertising already. So this is a Swedish study about menopausal hormone use in breast cancer. So like the exposure was menopausal hormone therapy, MHT. The people were divided into current users, past users, and never users. These are the sizes of the groups. These are the numbers of cases. Here is the risk that they reported. So in the current users, 38 per 100,000, and the past users, 20 per 1,000, and the never users, 17 per 1,000. And the risk ratio, well, this was chosen as the reference group, so you would just divide by the other groups with this risk. So this was among current users, breast cancer incidence was 2.2 times as high as in the never users. Among the past users, it was roughly 1.2 times as high. And here, well, this is the reference group, so you basically just divide 17 by 17 and get 1 automatically. Alternatively, you can express this as risk difference. How much difference is there between these risks? So 38 minus 17 would be 21 per thousand, or 20 minus 17 is 3 per thousand. And of course, here once again, 17 minus 17 is 0, so there's no difference. So this is just how you calculate simply the effect measures. Case control studies are pretty much as easy. Well, there are some probably not as intuitive thinking involved, but the mathematics is no more complicated. So basically, what we do is we divide the study population not in terms of exposure, but in terms of the disease status. So the cases are people with the disease, with the study outcome, and then we choose controls from the population who does not have the disease. And a major distinction is that typically in a case control study we would take everybody with the disease, while from the rest of the population we would only take a random sample. Also, what we are interested in is the frequency of exposure, not disease occurrence. Everybody has the disease here. It doesn't make any sense to calculate any occurrence measures. Nobody here has the disease, so it doesn't make any sense to calculate disease occurrence. What we're interested in is frequency of exposure, and this is expressed as odds that I already introduced. And odds ratio is simply a ratio of 2 odds, nothing more complicated. And odds, as I said, is just proportion exposed divided by proportion not exposed. So it's exposure frequencies. And odds ratio is the odds of exposure among cases divided by the odds of exposure among controls. So it's really, the mathematics is as simple as for cohort studies. It's just the logic of thinking that is slightly different. This study design we can also very simply express in terms of a 2-by-2 table. So here we have cases and controls, and they are divided into those with the exposure and those without the exposure. And we calculate the odds of exposure among the cases, A divided by B. And the difference being that we don't use the total here. And among odds of exposure among the controls, C divided by the D. And the odds is the ratio of these two measures. And okay, if we would be conducting a case control study within the same population, and then the question that we would be asking now is what is the odds of exposure in cases and in controls? And with the same data, we would just make slightly different calculations. Okay, odds of exposure among cases. Well, we have 3 cases, 1 is non-exposed. So 2 exposed, 1 non-exposed gives us odds of 2.1. This is not a proportion, this is a ratio. We don't use the total at all. So you can probably figure out now already what is the odds of exposure in controls. Using similar logic.
Какие шансы?
What are the chances of influencing the control? What are the chances? So anybody can calculate?
These people there are. Where do we
Мы
find them?
считаем тех, у кого
Yeah. So there are 6 cases,
у кого нет заболевания.
6 people who have the exposure are free of the disease, and then this would probably be a bit more. I'll have to go here. 31. So basically, we would just divide the number of exposed controls with the number of non-exposed controls. This is sort of a hypothetical example, because in real life you would probably not sample everybody without the disease. But in a real case control study you would probably take, 2 or 3 times as many controls randomly from the entire study population as there were cases. But if you're sampling them truly randomly and there's no selection bias, you would come up with the same numbers anyway. So the odds ratio, well, 2/1 and 6/31 would give us about 10. So here also we would observe an association of the disease and the exposure, just calculating it using different indicators. I think I'll skip this one. I've used enough time probably. Okay, so the cohort studies and case control studies are typically so-called non-interventional, non-randomized, non-experimental studies. In intervention studies, randomized trials, we would use slightly different measures of the effect. So basically, the key difference is that the exposure is an intervention. It is something that we willingly generate and apply to the population. But we could still call it exposure in the same sense. We could calculate the relative risk reduction, which is similarly, which is just a rate ratio -1. And what it tells us is which fraction of the baseline risk is removed. Or alternatively, we could calculate the risk difference, like we did before, and then from the risk difference, we can also calculate the number needed to treat, which is an important indicator of effect in randomized trials, which is simply the inverse of the absolute risk reduction. And the interpretation is that one outcome event is prevented per how many people. And what makes this slightly counterintuitive is the fact that the smaller the number, the larger the effect. If the NNT is 100, it means 1% of the people who received the intervention or were randomized to the intervention benefited from the intervention. While if it's 2, it means every second 50% of the people who were randomized or received the intervention benefited. So just another illustration. So we assume that we have a randomized trial, for instance. We have an intervention group and a control group. They are of similar size. There were 3 deaths in the intervention group and 6 deaths in the control group. So we can calculate these effect measures here from these frequencies. Basically, the treatment effect is, if you use the counterfactual thinking, that there would have been 6 deaths if there had been no intervention. If this was, let's say, placebo or conventional treatment, then it is the number of people who benefited is 3. We avoided 3 deaths from the disease because of this intervention. So we could, using the counterfactual terminology, we could say that 3 people would have died without the intervention. And we can just express these frequencies as pie diagrams. In the control arm of the 40 people, 6 died. In the intervention group, 3 people out of the 40 died. And so basically we could say that in the intervention group, there were 3 deaths that were unavoided, that were not helped by the intervention, and 3 who benefited from intervention, and 34 who would have survived even without the intervention. So the 3 people were those, actually out of the 40 were the only ones who received a benefit. And the relative risk reduction would be calculated as 6 per 40 minus 3 per 40 divided by 6 per 40. So it is 0.5. We halved the risk of death. It was 50% lower. Alternatively, we can calculate the absolute risk reduction by subtracting the risk in the control arm from the intervention arm. It is 3 per 40, and the NNT, as I said, is 1 divided by the absolute risk reduction, so it's 40 per 3, so it's 13.3. And so we would say that 1 out of 13.3 patients benefited from the treatment, and if you generalize it, will benefit in the future. But actually this is rounded upwards always, so we would say the NNT is 14. We need to treat 14 people in order to benefit 1. Just another example. Slightly different numbers. This is just for your information, more or less. This is just the same methods, just the same message as in the previous slide. So basically, we have two risks there, and then we can calculate the risk difference or absolute risk. Risk reduction, this should be, which is 0.1 here, and the risk ratio 0.75. The relative risk reduction is 0.25, and the number needed to treat from the risk difference is 10. So this is very simple and elementary. Okay, and then I'll just conclude by summarizing what I was talking about today. So basically, whenever there is a study that you are planning, I think the study question is of utmost importance, and that where everything should start, and everything else should be contingent upon the study question. So the study question should define what kind of design you are using in your study, and design means just sampling. How should you select the study subjects? And then on the analysis should depend on the study design, and the measures of effect and occurrence should also then follow the study design. But basically, the message here is that study question is the first and foremost issue. Prevalence is used to indicate disease burden in the population from existing cases, and it's useful for resource allocation and planning and those kind of purposes, while for etiological studies, we would nearly always use incidence. And this is a measure of appearance of new cases in the population. For a cohort study, we can use rate ratio and risk ratio, while in a case control study, we need to use odds ratios. And in randomized trials, measures of absolute effect should also be reported, such as absolute risk reduction, and it can be very neatly expressed as number needed to treat. Thank you.
Thank you very much. I think we'll skip the question part. We'll try to discuss it during the practicals.
Okay.
And I give some comment. Все, что рассказал, на самом деле.
So actually, if you open any magazine, you'll find 95% of data there. It's here in the article. So the current requirements are as follows. In order to get published, you will have to follow all these criteria. So it's simple and difficult at the same time. It's only the beginning. Actually, these measurements are associated with a number of problems we have to eliminate in future. But first of all, you have to learn to select analytical measuring tools for your studies and to learn how to calculate it. Actually, it's either deduction or division, but you can easily make a mistake here. Even outstanding scientists do make mistakes. This is one of the most important lectures in the course, and we shall distribute this presentation so that you can improve your skills. All the rest you can outsource from the statists, but